Okay. All right. So today we want to continue with integration. And well, yesterday was really a lot of fun. We got this notion that we could actually integrate, find the volume underneath the curve of a two variable function. And similarly, as we'll see, we can do things with functions of more variables. However, it may have been a little unsatisfactory to some because, well, one of the good things about moving up a dimension is that your domains become a lot more flexible. So in one dimension, you just have an interval. In two dimensions, you have any sort of, you have a disk, you could have all kinds of regions in the plane, and you may want to integrate over those regions. So today we're going to take what we learned yesterday and extend it a bit so that we can integrate over more general regions in the plane. So let's do a little bit of a warm-up, and we're going to sort of build to this more general integral. So the warm-up is just a silly, obvious fact that you know from one variable calculus, that if you have a function, if you have an interval, a, b, and then you have a sub-interval, so a prime, b prime, where these guys are inside, you could take a function that's sort of piecewise continuous, where it's maybe looks like something like this, and you have this sort of drop here. And then so maybe I'll make it a sort of, I'll make the graph red. I'll set it 0 off of this subinterval, and I'll take it to be some kind of, continuous function on this subinterval a prime to b prime. Well, this is kind of an obvious fact that if I think, if you're thinking of area under the curve, that this integral, let's say this is y equals fx dx, that this integral is the same as just integrating from a prime to b prime. There's no area under these the curves over here. So we can just go to this subinterval. So we want to use that fact along with Fubini to understand integrals over more general regions. And so how do we do that? Well, we use another fact, which is a little more difficult to prove, but it's true. And I'll just state it as a theorem. So a function f of xy with discontinuities, so it's continuous everywhere except along a smooth curve or piecewise, scam likely. No. I never talk to Mr. Likely, ever. Gosh, I don't know, yeah, it's the worst. I thought I turned that off, I don't know. Technical issues, sorry. All right. Okay, so a function f of xy with discontinuities along a piecewise smooth curve is integrable. So by which I mean it's integrable on closed domains, closed bounded domains. So I said last time, if you have a continuous function, it's integrable, but you can also allow for discontinuous functions so long as those discontinuities are sort of controlled. They just occur along some kind of, curve that you can draw with your, with your pencil or something. So Now, what we want to do is we want to take A, I want to think of B, and we want to add Fubini, and we're going to get integrals over more general regions. This is the idea. So let me explain. Now, how general do I want it to be? Well, let's see. Let's do a problem, and we'll do this by example in a sense. And so let's let D be the following domain. It's going to be the set of points x, y. I'm just going to use set notation here, but this is just the set of points x, y. If you don't want, you can just kind of think of just the inequalities if you want. X is between 1 and 2, and negative x is less than y is less than x. Now, the problem would be to compute the integral, double integral, over this domain, which is not a rectangle. It's no 2x squared y d. Double Riemann integral. Okay. So I'm going to give you the formal kind of picture in a second, but let's just work through this problem and see what we can say here. So the first thing that you want to do in a problem like this is you want to figure out what your domain is, what it looks like. That is, I think, the hardest part of these problems. And for not just this section, but the sections when you do other integrals over different domains. It's really trying to understand what your domain is. Once you have a hold over that, most of it's automatic computation. It's not too bad. So let's take a look. Let's draw D. Well, look at the plane here. Draw some, this is my domain, it's x, y. Man, Scam is loving me today. Worst. Okay, I gotta go to my settings and turn this off. I don't know. Okay. All right. So let me continue. So what we want to do is we want to take the first set of inequalities, x is between 1 and 2. That's not hard to write down what we get here. We have this bound, say at x at 1, this bound, say at x at 2. Bring it up a little. So x equaling 1, x equaling 2. So since we know x is bound by these two, we know that our region is going to be contained in here. Now, if you think about what you do, about what I did there, is I set each of these inequalities to an equality, right? I set this into an equality and this to an equality, and then I sort of use the inequalities to say what my constraint is on my x coordinate. So the point is if you have other inequalities, you want to do the same thing. So here we have these inequalities, and what we'll do is we'll draw when they're actually equalities. So when they're actually equalities, we get the lines x equals negative, or well, y equals negative x and y equals x. So y equals negative x is this line. And then y equaling x is sort of this line. Roughly. And so once we have all of that, we know what our domain looks like. We have this kind of picture. Now, this is not a rectangle, as I said. So what do we do with it? Well, what we can do is we can make a rectangle. So I can make a rectangle like this. Just start up here. square. Hopefully we'll, okay. And make a rectangle here. Okay. Now what I'm going to do, oops. It's the worst. Okay, here we go. So this is not wanting to do it. All right, sorry guys. I'm just going to freehand this. Let me make the rectangle. So what I want to make is a rectangle. I want to look at these bounding lines here and here. Okay. Good. Now I've got a rectangle and my domain is not the entire domain. But now what I'm going to do is I'm going to define a new function. So define, I'll call it f tilde on this rectangle. And this rectangle, as you'll see, as you will no doubt note, is going to be 1, 2 cross negative 2, 2. So this, what is it going to be? F tilde is going to equal one of two things, 2x squared y on D, and then 0 off of D. So it's just like what we did in that A. So we have some function now that's defined on the rectangle, and we're going to integrate that function on this rectangle. I'm really popular today. How do I, okay. Now you all can help me. So what do I do? Control. I'm sorry, do not disturb. Yeah, do not disturb. Thank you. Okay, extra credit. Sorry. Very disturbable, apparently. Okay. All right, so good. So this is this new function, and we want to integrate. Now we've got a function, and as I said in B, this function is integrable. The only places where it's discontinuous on this is right here, where it just kind of drops to 0. And so now we can apply Fubini, because we've got an integrable function on a domain, on a rectangle, and we go ahead and integrate it. So we're going to take double integral of 2x squared y over this domain D, dA, is going to equal this double integral. And here we have to make a choice. And I'm going to choose to integrate with respect to y first. So I'm going to go f tilde of xy dy dx. My endpoints, since I've chosen to do y first, my endpoints are going to go from -2 to 2, and then 1 to 2. Now, let's take a look at this iterated integral now that we've applied Fubini and see what happens. So what I'm going to do when I do this iterated integral, well, let me write it the way I did last lecture. We have this, where we put this integral in coordinates, or in parentheses. What I'm going to do when I do this is I'm going to fix x, right? When I fix x, then I integrate with respect to y. So I don't think of x as changing at all. I just fix it. So what happens if I fix x? Well, I get a line. So x is some arbitrary value here. X equals x. And I'm going to integrate over that blue line, really from, sorry, I went a little too far here. I'm going from -2 to 2 here. But now we have this picture that's from part A, right? We have this picture from part A, where along this part of the blue line, the function's 0. And then along the in between, the function is this 2x squared y. So if we want an integral from -2 to 2 of this function, it's the same as the integral from this value of y to this value of y, of 2x squared y. And but what are these two values? Well, this line here this line is y equals x, and this line is y equals minus x. So what I'm going to do then is I'm going to integrate 1 to 2 minus x to x of f tilde x y. Oops. Well, I can do it this way, but I'll just actually put in the values here, so or the function here, 2x squared y. So what we see when we do this is when we're doing and when we're working with more general domains is that the functions that are bounding our domain enter in to the endpoints of integration. But again, these are sort of fixed. We're thinking that we're only integrating y here. We're not doing any integral with x. So let's go ahead and integrate. So here we'll get, so this is going to be x squared y squared. And here we're going from y equaling minus x, x, dx. And we'll put in this value. And you see that you get 0. X to the fourth minus x to the fourth. So we're done. So the key part isn't the evaluation of the integral. The key part is getting to this point. Well, really this point. Okay. Questions? Okay. So that's the trick. That's how we do more general, that's how we integrate over more general domains. So now what we want to do is see in practice what kinds of domains are really susceptible to this kind of approach, right? Sometimes you have to make a slight change, so on and so forth. So for that, we have two different types. We have type 1 and type 2 domains. And, of course, we'll see in a second, there are types that are, or there are domains that are neither of these. There are domains that are both of these. So type 1 region is a domain D, which is just going to be equal to a set of points x, y in the plane that satisfy two inequalities. One, x is bound by a and b by constants. A and b are constants. And y is bound by functions of x. So we'll call them g1 of x and g2 of x. Okay. Usually what you want of G is that they're nice and smooth functions. They're not like absolute value type functions or case functions or strange things like that. They're kind of nice. That's what you would like, but it's not necessary. In this case, Fubini's theorem, which we just used, we just had a case like this, says the following. Well, it's written up on the important concepts, but let me write it here too. It just says that if we want to take the integral of a function over this domain, and again, we'll assume this function is continuous on the domain, not on necessarily on anything else, then this is just equal to the integral from a to b, the iterated integral, where now we put the bounds of integration for y as functions of x. And here we'll have fxy, dy, dx. And a type 2 region is similar. Type 2 regions, however, their domains, instead of having bounds of y in terms of x, it's the opposite. So x is bound by functions h1 of x, h2 of x, h1 of y, h2 of y, and let's see if I can write legibly here, and y is bound by constants, say C and D. And again, we have a Fubini theorem here that if we take the integral, double integral of f over this domain D, then this is going to be this integral. Now you'll notice something, or at least I hope you'll notice something, and you certainly will after I say it, which is these integrals, now we're using Fubini's theorem. When we have a type 1 region, that's really only a type 1 region, or type 2 region is only a type 2 region, we no longer have this sort of symmetry that we can use, or this choice that we can make in expressing our double integral as an iterated integral. We sort of have a fixed order that we have to go through once we've made a determination of the type of region we're dealing with. There's, as I said, there are regions that are both, in which case you still have that ability, but you have to then express it in the right way. Okay, so let's take a look at a couple of regions. We'll do a, I think when I taught this last, I did a Zoom poll, but I'll just do a hand, well, I don't know, we'll see what people say. Okay, so I'm gonna see if I can give myself a parabola here. Okay, so let's do the following. This region, give you this. This region, and I have some strange region here, which I'll put up top. Okay, there we go. Okay, so now, 1, type 2, either, both. Okay. So this dotted line here represents the region. Okay, first case, what do people think? Type 1, type 2? Do I need to, I don't think I can fit the definitions and the pictures in. So what is type 1? X is bounded between two constants. Y is bounded between two functions of X. Type 1, type 2 for this. I have here 1, type 2. How many people say type 2? Raise some hands. Be bold. Okay, how many say neither? Nobody. How many say both? How many say type 1? Oh, type 1. I guess, yeah, in person, that's how the majority wins, and they're right. This happens every once in a while. Okay, this is type 1. The point is we can make this bound. Here are the constants. These are the constants, and then between them, we have these two functions. We have a function of that's sort of the upper function and a lower function, and everything is stuck in between. Okay. So X is bound, or Y is bound in terms of X. Okay, what about this guy? Neither? Okay, yeah, good. Everyone's right. I see a few people very subtly flashing me too. Okay, good. Correct. Guys, you guys are shy or something. Okay, right, two, right? So I can look at the bounds. Here's a bound. Here's a bound. No, that's the bound that's up, slightly up. And then these two functions are functions of y that bound x. Here? Neither, right? It's neither, right? I mean, the point is if I try to bound it, well, I have a, over certain regions, like this region, I have nice upper and lower bounds, but then all of a sudden here, I have, several functions that are sort of bounding it. And so this doesn't really fit into the type 1 or type 2 picture. And then both here. So that was not a very interesting puzzle because it but okay, well, it's tricky sometimes. So if you have both, you can, as I said, use either technique. And we'll develop other techniques that make it, well, that's sometimes you don't want to use this method, but okay, we're not there yet. All right, let's do another problem. I think, again, the hardest part of the problems of integrating over more general domains is really giving a description and making a decision on what type of domain you have, and then writing the iterated integral. In fact, in some exams, the question won't be evaluate the integral, the question will be express this as an iterated integral. So sometimes the hard part here is not computing an integral, it's setting it up. So let's do another problem. All right, so let's let this domain D be described as follows. So we'll say that y squared minus 1 is less than or equal to x, which is less than or equal to 4 minus 4y squared. And we'll ask ourselves to compute double integral of 2x over this domain D. So if you look at a problem like this, you will find that, sometimes these domains are not expressed in a completely obvious way as saying, oh, this is a type 1 or type 2. Unlike the previous case where we had constant bounds on one of them and then function bounds on the other, here we just have function bounds on one in terms of the other. And so there is a question here as to what kind of domain we have and how we want to write this as an iterated integral. So my suggestion, if you can do it, is to try to draw the domain D. There's other things you can try to do, but I think that's the most straightforward way of approaching this. Let's draw D. If you're a horrible artist, don't worry, you won't be penalized based on your rendition. It's more just being able to take this step so that you can write the correct version of the integral. Okay, so let me give myself my XY plane. And again, when I want to find a domain and it's expressed in terms of these inequalities, what I'll do is I'll take one of the inequalities and I'll set it to an equality. And that will give me sort of at least part of a boundary of my domain. At least, I mean, not always, but if it's set up, normally it will give me part of the boundary. So here, I'm going to look at the equation y squared minus 1 equals x. And that you'll recognize as an equation for a parabola, but now just thinking of x as a function of y. So this is just, if you kind of switch x and y equals x squared minus 1, you know how to draw that parabola. And so here, just do a, switch the x and y, reflect over the line. So this will give you this picture. Let me be colorful here. This will give you this picture. Something like this. More or less. Okay, so this should give us one of the boundaries of our domain. And now if we want the other domain, other boundary, we look at the other equation. We set this other inequality equal to an equality. So we get 4 minus 4y squared equals x. And when I look at that, so here I sort of labeled this, this intercept here is x equaling 1. And here again, you get another parabola, again, viewing x as a function of y. And however, now it's just sort of concave down rather than concave up. And its intercept is at 4. So we'll get some other parabola. Best here. This. Never get used to this. Something like this. I mean, this is not to scale, but this is the picture. Okay. And now what you know is x is stuck between these two bounds. So you know that you can kind of see what your region is. It's this region here. This is the region here. And why does that help you? Well, if you were able to successfully complete that last quiz of identifying which regions are which, here you can look at this and say, okay, what kind of region is this? Or what's best suited for an integral? And in fact, this is both types. However, one is better suited than the other. So what do people think? Which type should I use? Should I use a type 1 or a type 2 description of this region? Some people, I see type 2. Anyone want type 1? Okay, nobody wants type 1. Okay, good. I'm glad no one wants type 1. So the function for a type 1 would be not, I mean, you would have a break. You'd have to have a case function. So here it would be two different, I mean, it's continuous, but it's not a very nicely defined function. Whereas the function for type 2, you have sort of the blue upper boundary and the red lower boundary. So you've already have this expressed in terms of functions. However, you are left with having to find the bounds of the y coordinate, right? The constant bounds. So we are left with that, and you do need to do that. So how do you find these y bounds? Well, you look at the intersections of these two things. So we want y bounds. So y should be between C and D. Well, as I said, this happens when both of these curves intersect. So when we get this equal to this. So this occurs when 1 minus y squared minus 1 equals 4 minus 4y squared. Or just doing some arithmetic, this is y squared equals 1, or y equals plus or minus 1. So the bounds here for C and D are -1. So bounds are -1 and positive. So when you find these bounds, you're on your way. Right? Because now we have sort of we can put these two things together. We can look at Fubini's theorem for these different regions, and we know exactly how to set up the endpoints of integration for our iterated integral. So let's do that. Fubini tells us that this double integral over d 2x dA is equal to an integral from -1 to 1. Here's the integral we're going to perform with respect to x. We're going to go from y squared minus 1 to 4 minus 4y squared of 2x. Dx dy. Now, let's go ahead and, so now that we've got everything set up, we've applied Fubini, we've done the hard part. And if you're taking an exam, as you will, and you have a question like this, you get here and you're successful, sometimes that's the end of the question. And sometimes, and in the case where we actually want computation, you will get, 7 out of 10, 8 out of 10 for getting this far. So this is really the hard part of this process. Okay, so now we just integrate. Maybe 7. we do want to see a little bit of it. Make sure that we're doing it. Make no promises. I will say in these problems, there is sort of hidden efficiencies. They're not, and again, here I should probably say x equals. There are hidden efficiencies. So, which I try very hard when I'm writing exams to put into problems. I don't want you to have to take a long time on some of these problems. So I put things in to make them quick. This would be an example of that. So here, what people will do often is they will put in, they will put in these values, which is fine. And now you'll notice again, and this is all fine. However, you'll notice that x is no longer there. Good thing to check at this stage. But what people will often do, which is, I would say, sort of a mistake, is they'll start expanding squares, right? And then doing a whole bunch of stuff. It's a natural instinct, but I want to say, slow down, take a look, and realize something, that this is 4 times negative of this. And so maybe I would say a slightly faster way of doing it here is pull out the 4, or -4 if you want, and square it. And then realize that you don't have to do that, and you can just get 15, well, y squared minus. We bring the 15 out. And here, here you may want to expand. But I'm just saying that if you notice things like that, you kind of cut your time almost in half. And more importantly, you'll reduce errors. Yes, question. Yeah, that's a good point. So so the gentleman in the back said that if you, well, actually, I'm not sure I understood you. So what are you saying? I think you want to use symmetry properties here, which is, if you had odd functions would be great. I would encourage people to do exactly what you're trying to do, which is to look for symmetry. I do put those in sometimes. And so, but here we have even functions, so I think we're not going to be able to do that. Well, you can do something, but I don't know. Okay, anyway, at this stage, it's just computation. Y to the 5th over 5 minus 2/3 y cubed plus y. And again, we're evaluating from 1 to -1, so we'll just get 2 from 1 to 0. So I don't know, 30 times, I don't know, you guys can figure this out. I'll let you make common denominators and such. Okay. So I don't, don't follow my example. If you're on an exam, please do actually evaluate the number, but okay. I'll try not to give you kind of ones that take too long. All right, so now I want to do one last problem, which is really a lovely problem, but does take, well, let's try to set it up. I'd like to set it up. So find the volume of the standard. I'm going to call it the 3 simplex because the student told me that calling it what I normally call it is not technically correct according to, well, I don't know, according to the hacks that write Wikipedia. So for I think there's shapes called the Platonic solids. Who knows the Platonic solids? A couple. So the Greeks were a little crazy, especially the mathematicians. They had real psychological problems, as most mathematicians do. And well, so they thought that there was like, this spiritual meaning behind regular solids. And so the regular solids are things like, this is the tetrahedron. And then, you have the cube. And then, okay, there's a couple more, 3 more. Do people know any of them? Huh? Octahedron, very good, yeah. Octahedron, as you might guess, is like, has 8 sides, 8 faces. It's like little. Any others? Oh, I love it. So you guys warm my heart. I'm not going to draw the dodecahedron. The dodecahedron, and then the one that's kept from the masses, like literally, they would not allow it to like be disseminated because they thought people's brains would explode. I'm paraphrasing, but was icosahedron. Icosahedron. Anyway, they kept all of these secret. Well, not all of them. The last one is like, and there's some beautiful pictures like Kepler's has this picture of, the orbitals of the planets, everyone thought all sorts of mysterious things. Anyway, mystics. They're beautiful shapes. It has a lot to do with mathematics and really interesting. And they do have some things to do with chemistry and things of that sort. But the tetrahedron is this guy. It's the most simple. It's sort of like the three-dimensional triangle, if you will. Very, very essential in a lot of mathematics. So what do I mean by the standard 3 simplex? Well, it sort of has this shape, but it's not regular. It's not, doesn't have all the symmetries that this has. So what is it? So I'll describe what it is, just visually. So we go to 3 dimensions, and I'm going to take the standard basis vectors, right? I, j, k, and I'm going to take the origin. So this is k. I'm just going to draw the endpoint, j. This is I. And of course, the origin is here. And I'm going to connect all of them. So we'll do it with red. And then I'll just fill everything in. Fill in that shape. That's the standard sim. So actually, this is kind of a projection of the standard simplex, to be honest with you guys, but you won't, don't worry about it. So find the volume of this thing. Find the volume of it. That's the question. Now, if you've had a good linear algebra course, you probably know how to do this already. But who has had a good linear algebra course? That was a rhetorical question. So for us, we'll set this up as a double integral. So the point is if we think about this shape, we can look at the bottom and we can think of this as the volume underneath the graph of this function, which is the top, right? Which is this top. And we'll see if we can find that volume. So for that, we would need this function. Now, the question I have for you guys is, what is that function? So I'm saying there's a function that gives me this top, whose graph is this. What kind of function is it? Yes. Okay, great. So that's an equation, but you can use that equation to find the function. So there, let me just, I was hoping for a more vague answer. That's a very precise and correct answer. The vague answer that I want as an in-between answer is that this thing is going to have the equation of a plane, right? We can imagine extending that out, right, all over 3 space, and we'll get a plane. So we know what equations for planes look like. And if you think about it, well, we have 3 points on that plane, and you can go ahead and use the techniques from the first part of this course to find that equation. When you do that, you'll get the equation that was just mentioned, x plus y plus z equals 1. Now, if we want to express that as a function, we can see that we get this function. So let's take this blue domain, call it D, and we'll integrate. So we want a double integral over this domain of f of xy. And that should give us the area, the volume of this tetrahedron. Okay, so now we're in this situation. Let's draw this domain D in 2 dimensions and see what we have here. Well, we had I and j, and we connected to the origin, and we filled in. This is our domain D. What kind of region is this? Huh? Type 1? That's it? Type 2? Both? Type 3? It's both. It's both. It's a choose your own adventure situation. So we could do type 1. We do type 1. Well, we can see what the bounds are for x. X is between 0 and 1. And then y is going to be between this function, which is constantly 0, and this function, which is y equals 1 minus x, as you can see. So now we know exactly how to write this out. It's the volume going to equal this double integral from 0 to 1, from 0 to 1 minus x, 1 minus x minus y, dy dx. And I just hit time. If you calculate this out, which is not a hard calculation, you'll get 1/6, which is also 1 over 3 factorial. If you want the n simplex, standard n simplex, to find the volume of that, that's 1 over n factorial, by the way. All right. See you guys on Tuesday. Have a good weekend.
Yeah, I put it up, but it was a little late. I'm sorry about that. Yeah, but it's up.
Yeah, because I missed Tuesday with 6, so.
Yeah, sometimes I forget it during the day and then I remember at night.
Okay, no worries, thank you.
Yeah.